Hey everyone, we want to take a look at this planar motion and the relative motion that we've talked about in a previous video. And we want to take a look at it in this situation. This is what's referred to as a sun gear, or planetary gear, excuse me. It's referred to as a planetary gear. So I've got a central gear that you see here in purple, and then around that is being another gear. The red gear is moving around that in some circular fashion. And then the black gear is actually another gear. There'd be teeth on these in the actual thing. But we're going to consider these three gears in contact with each other, and they're all toothed up. For simplicity, we're going to start this with the purple gear being stationary. So it's not rotating. The purple gear is not rotating. But there's a blue bar here connecting the center of this system, all of these gears, the center of these gears with the center of the red gear. Okay, and what we want to look at are the relationships between these velocities. Okay, so let's designate a couple of things for starters. So we're going to say that, well, this is position O right here. And so I'm going to call this point up here, we'll call that B. And let me actually label this A instead. I think that'll be a little easier. So A is stationary. So then there's B. I'm going to take a point right here, and that's where the red gear is being driven along the purple gear. Now again, the purple gear is stationary, it's not moving, but AB is rotating, and for simplicity, we're going to have it rotate in the counterclockwise direction. So there's another point right here, and that point is C, and then finally there's another point right here, and that point is D. And what we're interested in is the velocities of everything that's taking place at these three spots. So again, the velocity of A is equal to 0. This is a stationary point. And I can consider that my origin. That's why I had it as O before, but I think I'll just use the letter A for now. Okay, now AB is rotating, and so there's this omega AB, and it's going to be in the k-hat direction. Right, so it's going to be rotating in the counterclockwise direction. It's moving with some constant angular velocity. We'll keep it constant just to make our life simple. And so that's going to cause the red gear to roll, if you will, around the purple gear. And what I'm interested in is how fast is it rolling, and what else is going on here. So there's a speed of the gear as it rolls. And then D is also going to be causing a rotation of the black gear. That's kind of what we're anticipating is going to happen. All right, so let's start one step at a time. So we've got A, so now let's go to B. So the velocity of B with respect to A, that's going to equal omega AB, and again, that's in the k-hat direction, crossed with the position of B with respect to A. All right, so the position of B with respect to A. And I could have an XY coordinate system in here. This might be my X, and this might be my Y. And we'll do it that way just to kind of make it more generic, if you will. And so the position of B with respect to A, that's going to be determined by some angle in here, which I'm going to call theta. And then the length, how far is it from A to B? Well, the length from A to B is the radius of the purple plus the radius of the red, right? That's the distance. So R of B with respect to A, if I write that in polar form, it's the radius of purple plus the radius of red, all at some angle theta. And so I can find the velocity of B with respect to A by doing the cross product of these two. Right? I'm not going to do that because I don't know specifically what theta is and what those R's would be. But if I had numerical values for them, that would not be a difficult thing to do, to take that cross product. And we would anticipate that we would have a velocity of B, and it's going to be, it better be at any rate, the velocity of B with respect to A must be tangent to the circle that B is making around A, right? Because it's forced to follow that circular path. So the velocity's got to be tangent to that circle. All right, so if I extend my X and Y axis up here, velocity is in this direction, then it's going to be perpendicular to that. So let's see, how do I do this? I know that this is along AB, and this is some angle theta, right? And then this is perpendicular. So the velocity of B with respect to A is going to have some speed, VBA, and the angle will be theta plus 90 degrees, because it's forced to be in that perpendicular, that tangent direction, right? Perpendicular to theta. Okay, cool. Well, remember, tangent is always perpendicular to the radius. That's how I know that that's 90 degrees. The tangent to a circle must be perpendicular to the radius of that circle. Okay, so that information then will give us the velocity of B with respect to A. That's pretty straightforward. And now let's take a look at the velocity of C with respect to A. So the velocity of C with respect to A, that's going to equal the velocity of C with respect to B plus the velocity of B with respect to A. So I've done this, that part we've already done. Then there's the velocity of C with respect to B. And if we think about that, as this thing rotates, the red gear is going to rotate like this, right? It's going to, because it's rolling. As this thing goes in the counterclockwise direction, the red gear is going to roll along that gear. So it's going to have some omega value, which is also going to be counterclockwise, right? And so this right here, this right here, the velocity of C with respect to B is going to equal the omega of the red gear. So I'm just going to call that, well, let me call it omega BC. That's the omega of the red gear, crossed with the position of C with respect to B. Right, the position of C with respect to B. But the position of C with respect to B can come back this way. Right, now, coming out there, that was the angle theta, so this is going to be theta minus 180 degrees because it's pointing in towards the center. So this is going to be the radius of C with respect to B, but that's red radius. So that's R sub red at an angle of theta minus 180 degrees because it's coming into the center, in towards the center. So it's exactly 180 degrees in the opposite direction. Right? And then this is just going to be some omega BC in the k hat direction. Okay. So I don't know the velocity, and technically right here I don't know what omega BC is either. But let's think about this, because we talked about this when we talked about the rolling disk. As this thing rolls, it's right here on C. As the gear rolls, the position of C, the velocity at C is 0 compared to the purple disk. Remember, the purple disk is stationary. The purple disk is stationary. In this case, now it could be in other cases where the purple disk is not stationary, but in this case, the purple disk is stationary. And so the velocity of C, if it's stationary with respect to the purple disk, it's also stationary with respect to A. So the velocity of C with respect to A, that must be 0. And so I can find some of this information by putting it into this equation. Right? I have to put this one into the velocity of C with respect to B. I know the velocity of B with respect to A. There's a few unknowns in here, but this is equal to 0, so I can solve that systems of unknowns. Keep in mind, this is a vector. So there's an I component and a J component. So you really have two equations. So we have room for two unknowns in this scenario, because you're going to set the I factors on the left side of the equal sign equal to the I factors on the right. I components is probably what I should say. And the J components on the left side equal to J components on the right. So that's a system of two equations. And so theoretically, we would have two unknowns and we can solve that out. All right, so that's going to get us to that point. All right, we'll stop there and then we'll take a look at D and what's going on up there here in just a bit.